Hello everyone, this is Xiao Peng from Int'l. This talk is about the application of constraint programming in non-crossing MAPF problem. Today, the multi-agent path-finding problem is a very active research topic, which is widely applied in the industry, like the transport in some fulfillment centers. As we can see in this picture, there are a team of robots to accomplish pickup and delivery tasks in a warehouse. Each robot moves from one point to another point without any conditions. For such a classic MAPF problem, the objective is to plan a collision-free path for all the agents, and the optimal solution aims at minimizing the makespan or the total traveling time. In this work, we consider an extension to MAPF for tethered robots, and we call it non-crossing MAPF problem. It's motivated by a real industry application that a fleet of tethered robots are used for inspecting large structures. Compared to the classic MAPF, the main difficulty is that the robots are not able to cross cables. Like in this example, there are 3 robots and 3 target points in the workspace. Every robot is attached to an anchor point by cables. As the red and blue cables are crossing, so it's not valid in our case. We assume that the cable is always kept taut while robot is moving. Therefore, when we talk about the shortest path, it's also the position of the cable, and the targets are not assigned to the agents in advance, so it's anonymous. We consider this new MAPF problem in a continuous workspace, and we suppose that the obstacles are all polygonal. Then the visibility graph is natural for us to think out, and it can be constructed in polynomial time. The algorithm used to solve the classic MAPF, like CBS, is not suited to solve our problem because this approach is efficient only when conflicts are easily resolved by small modification to the path. However, it's not in our case. If each time we resolve the conflict by sequentializing the motion of robots, then the makespan will be dramatically increased. So, our strategy is to find a non-crossing path in the graph. We develop this problem into 2 classes. One is the case where no obstacles in the workspace, and the other one is the case with obstacles. In both cases, I will present how to compute a lower bound and upper bound as well as the optimal makespan, and I will also show you some experiment results in each case. Firstly, we consider the non-crossing MAPF without obstacles. As shown in this picture, there are no obstacles in the workspace, and there are 2 sets of points. The red one is the anchor point, and the blue one represents the destinations. The idea is to find a one-to-one matching between them with a minimum makespan, and the solution cannot contain any crossing edges. To find the solution, we begin with studying a well-known problem, the linear sum assignment problem. We can also call it LSAP. So what is LSAP? Based on a bipartite graph, it aims at minimizing the sum of the costs of the selected edges in a matching. And it can be solved in polynomial time by Hungarian algorithm. The good news is that the solution of LSAP cannot have crossing edges if the cost is defined by your Canadian distance. As we can see in this picture, every red point is assigned to a blue point, and there is no crossing edges in the solution. Because if 2 edges cross, then we can always obtain a better assignment by swapping their destinations. So the two edges no longer cross. However, the bad news is that LSAP doesn't minimize the makespan. Therefore, LSAP can provide an upper bound for our problem. Another interesting assignment problem is a linear bottleneck assignment problem as LBAP. And the objective is to minimize the maximum cost of a selected edge in a matching. This is also the definition of makespan. It can be also resolved in polynomial time by adapting Hungarian algorithm. However, the bad news is that the solution might contain crossing edges. As we can see in this example, this edge and this edge, they cross, so it's not a valid solution for us. If we impose the non-crossing edge constraint, then LBAP becomes NP-hard. So the solution of LBAP provides a lower bound. The upper bound computed by solving LSAP can be improved by performing local search. Here, we propose a VNS framework. Since the solution of LSAP is feasible as it contains no crossing edges, so we can begin with the solution of LSAP. In this VNS algorithm, the neighborhood of a matching contains every non-crossing matching obtained by permuting the destinations of k anchor points. As we can see in this diagram, we first search for the longest edge. In this example, it's the red edge from A1 to D1. Then we enumerate all the subsets that contains k-1 anchor points different from A1. And for each subset, we consider for every permutation of the destinations that without crossing edges until we find a permutation whose longest edge is smaller than A1 to D1. If such a permutation could be found, then we can update our solution and reset k to 2. If not, we increase k. We repeat this step until a time limit is reached, or k becomes greater than k max. To find the optimal solution, we introduce a CP model to solve the problem. In this model, we have a set of variables xi as the destination associated with each anchor point ai, and another variable y represents the makespan. And there are three constraints. Firstly, for each pair of anchor points ai and aj, we post a table constraint on the destination pair xi and xj. That's xi not equals to xj, and the edge ai xi doesn't cross aj xj. Secondly, the length of each selected edge should be less than y. And the last constraint is all different constraint on xi. In fact, this constraint is not necessary, as the table constraint can prevent two x variables have the same value. However, in the experiments, we found that it can make the solution process more efficient, so we keep it. We evaluate our algorithm on simulated instance. Here, UBI-CP means a sequential combination of LSAP, VNS, and CP. We firstly compute an upper bound by solving an LSAP, and then improve it with VNS. The parameter I here refers to the K-max in the VNS. And finally, we can apply a CP model to compute an optimal solution. there are 4 caps in the result, and we can take the example of the orange one. All the caps begin with the solution of LSAP, and then the cap drops. This is because of the step of VNS. And then we observe a horizontal part, and this period is to generate the CP model. And after this horizontal part, the cap drops again. And this is because the CP model improved the upper bound. We can compare the 4 caps. When I increase, and the VNS can compute a smaller upper bound. However, it takes more time. As a counterpart, with a smaller upper bound, the time spent to build a CP model and to find the optimal solution also decrease. So the important thing is to find a compromise between the time spent on VNS and the CP. From the result, we can see that the green cap as UB5CP performs the best compromise. And now we can see the case where the workspace contains obstacles. In this case, the difference is that from one anchor point to another destination, there might exist more than one possible path. Here we introduce a new definition, homotopic path. 2 paths are homotopic if there exists a continuous deformation between them, without crossing obstacles. In this example, the paths tau1, tau2, and tau3 are of the same homotopic class. We can transform tau2 to tau1 and tau3 to tau1 without crossing any obstacles. Because the cable is always taut, so we consider only the shortest path of each homotopic class, as the red path here. And from point S to point T, there are at least 3 different paths. And we can perform a depth-first search to find all the relevant paths in our problem. Why should we enumerate all the relevant paths? Because sometimes the optimal solution may contain no shortest path. Here we have an example. On the left, the green path and the purple path are all the shortest paths from the anchor point to the destination. However, the makespan in this case is not optimal. And on the right, we exchange the destination, as this anchor point is assigned to this destination. The purple path is always the shortest path. However, and to avoid crossing the purple path, we plan another green path, which is no longer the shortest path. But in this case, the makespan is optimal. In this paper, we are able to prove that giving an optimal solution of LSAP, we can compute in polynomial time a solution of the same total length that has no crossing path. Let's consider 2 crossing paths pi n and pi j, the red path and the blue path here, as a part of the solution of LSAP. For the example on the left and in the middle, we see that the segments UI, VI, and UG, VJ cross at point X. And this crossing can be removed by swapping UG and VI. And now the red segments UI, VI is replaced by the green one UI, VJ, and the blue segment is replaced by UG and VI. According to the triangle inequality, we know that the sum of the paths are reduced, and this is a contradiction with the fact that the solution of LSAP minimizes the sum of the cost of the paths. For the example on the right, pi and pi j don't contain any crossing segments, but they cross at V2. In the same way, we can exchange Wi and Wj, then the two paths will not cross anymore, and the sum of their lengths stays the same. The interest of this theorem is that we can always find a feasible upper bound by solving the LSAP. Similar to the case without obstacles, this upper bound can be improved by VNS. The only difference is that when searching for the neighborhoods of a matching, since there are sometimes more than one feasible path between any anchor point and the destination, as shown in the diagram, from K to D2, there are 6 or 5 paths. In order to reduce the complexity, we only consider the shortest path, the green one here, when we compute the VNS. We can also construct a CP model to find the optimal solution. Compared to the case without obstacles, we have to consider all the paths between any anchor point and destination. So, in this model, we introduce a new variable as Zi, associated with every anchor point Ai. And its domain is the set of all the paths starting from Ai. As a result, we impose a table constraint on Zi for any pair of paths Zi and Zj, starting from different anchor points Ai and Aj. They should end up with different destination too. And at the same time, they don't cross. For the experimental evaluation, we consider two kinds of simulation, and they are all motivated by real application scenarios. The first one is that anchor points and destinations are randomly generated according to a uniform distribution, and we call it U instance. And the other one is B instance, that the two sets of points are generated on the left part and the right part of the workspace. In this slide, we display the result of optimal makespan, the lower bound, and the upper bound in each case, as well as their evolution when the number of the obstacles increases. In both cases, we observe that the number of the obstacles has no significant effect on the optimal makespan. And for the B instance, we can see that VNS doesn't improve much the upper bound, whatever the value of Kmax is. But the optimal solution is much smaller than the upper bound. It means that we need to use more non-shortest paths to improve the solution for B instance. And for the evolution of the gap to optimality, for U instance, the result is similar to the case without obstacles. The difference is that LSAP takes more time to solve. It's because that the function to check if two paths are crossing or not has a quadratic time complexity. On the right, for B instance, the horizontal part is longer than the case of U instance because VNS doesn't improve much the upper bound, so it takes more time to find the relevant path and to generate a CP model. In general, the B instance is much harder than the U instance. To conclude, in this work, we introduce a new kind of MAPF problem as non-crossing MAPF for tethered robots. To solve the problem, we were able to compute the lower bound and the upper bound in polynomial time. We also proposed to sequentially combine VNS and CP to find the optimal solution. For the future work, we plan to test other methods like tuple search and integer programming. We also consider to extend this work to non-point able agents by considering the physical size of robots. Thanks for your attention.